All right. Morning, everyone. Thank you for joining us in our RC design class again. Today will be our last lecture. We will go quickly over one typical example of a design drawings. Well, this is called design A drawings from the textbook. And we also do a sneak peek of what the final exam will look like, at least from the overall types of problem that you'll see in the final exams. Okay, now before I get started, several quick announcements. I have posted quiz 10 online on Canvas. So before the deadline, and please upload your solutions. And the homework number 8, I also uploaded, and that homework is now collected. Okay, so you see from the title, that homework is now collected. Okay, so you can utilize your time to work on it. But if you have questions or want to go over them, email me and we can schedule time to go over them. All right. Now the final is determined to be between 2 p.m. to 5 p.m. on that Friday, 14th. Folks, give me 1 second to close the door. The noise out there. All right, sorry about that. I'm back. The finals, like I said, again, is 2 to 5 p.m. May the 14th on the Friday afternoon. I have few students that are taking a different time. So I send a reminder next Monday or Tuesday and to schedule a different time for you. So we'll set up the same assignment or exam tab on Canvas like we did for the second and the first midterm exams. Okay, now you'll be upload your solutions online directly. And about the lab design, the lab design is going to be in part of the homework and it will be treated as part of homework gradings. So for go to Canvas and see that there's a tab called lab design. So the deadline is May the 14th, 11:59 p.m. Okay, so right at the last minute of the Friday. All right, so that's all we have left for the course. And one more thing is about the response rate of the survey, the CET evaluation, excuse me. So we have right now about 50% response rate, a little bit shy from the 70% target that we set. So please, if you haven't responded that, please respond that. If you know your friends haven't done that yet, please respond that. It's a fairly painless survey, right? It only takes you about a few minutes, unless that is if you have a lot to say. But if you do have a lot to say to this course, please go and fill the survey. I will see them and I'll make improvement based on your feedback. I got pretty good feedback from previous semesters, and I utilize a lot of notes to improve the lecture this semester. There are a few things I want to employ, but based on this teaching, not in office setting, that I have to defer that to next semester. But if you have any suggestion for the future as well, that I imagine in the classroom setting, you can also fill out the feedback. And if you have any concern that during this COVID experience in the lectures, also fill out in the survey. All right. Now, one more thing about the grading. So I guess that's what we'll worry about, right? The final grading. And I will say this way: I have looked at all your grades right now, except the last quiz, and which I hope I can receive that and get your grades next week. And you suppose we'll see most of the grade before the final exams, right? So I see that, and I see a very good distribution in the class, meaning that we have a lot of A's, we have a lot of people in the middle as well. Very few people on the failing end of the spectrum. So I'm pretty happy about the overall results so far. So as long as we do a good job in the final, don't tank it, and I don't think we have any issues. Excuse me. Sorry. Then I don't think we have any issues. Okay. So about the finals, right? So let me just share the screen. Go ahead, share the screen with you quickly before we go into the design diagram. I pull out the final exam from 2017. This is recorded, so you don't have to rush in and take photos and that. You can go back to take a look at it, but please don't spread it around, okay? This is in 2017, and first part we gave an irregular section where we have openings. Now, we have tested irregular section in exam 2, so I don't think we see this problem. I mean, identical problem. We have to change it a little bit. Now, if you look at this problem, the challenge is that not only we have a narrow section, but we have opening in the flange. We have opening in the flange. But as soon as you realize that since the compressive zone does exceed the flange, so it's getting a little bit more complicated, you actually have to find the regions and then find the centroid of the compressive zone and do the flexure calculations. Okay, so this is just one big part at the beginning. This format deterred quite a bit of students back then that you would not expect to see that. So once they saw this as a big problem, the first one, they were a little bit worried. But we'll try to avoid this format. Basically, still give you multiple choice first. Okay. Now here's a multiple choice session, so you can read out. So precast concrete being exposed to weather, contact with ground. So we were talking about minimum concrete cover, right? We have the bars as well, that is the stirrups, and purpose strength reduction factor phi. All these are pretty, I wouldn't say trivial, but you have seen this before in exam 1 or 2, so nothing fancy, right? But there was some added problem from the later section of the lecture, right? This is the deflection calculation coefficient. I call it C or epsilon, right? So either way, this is the coefficient that you need to determine. Remember, there's a drawing, right? If I can annotate here, so you can see that usually it's in terms of a y-axis like this, and axis in terms of time. And we have months, so 3, 6, 12, etc., so on and so forth. The maximum is 16 months, 5 years, right? And this is C or epsilon. And then you have a more of a curve like that, right? And plot 2 is at 2.0. Plot 2 is at 2.0. All right, so if you forgot, how do we determine this, and go back, take a look at it, right? But essentially that is, you can find the C based on the 12 months, based on 12 months mark. Now this exam here, I did not provide this graph here, but in the exam, in this final, if we were asked you to find out the C or this epsilon here, I will provide this drawing here for you to do that. I will provide this drawing here for you to do that, so you don't have to remember it. But again, you have all the resources at your disposal. It's open book again for the finals, okay? So it's open book again for the finals. So you should be able to refer that and find it, okay? All right, so that's that. The next one, which of the following mechanisms shear transfer in the reinforced concrete beams without shear reinforcement, right? So this is more conceptual. The shear, again, you have seen this, you should have seen this, and just pick out the right answers, right? And compute a modular ratio concrete specified compressive strength of 5,000 PSI. This is talking about N, right? Talking about N. So got to think about what is N, right? That is the ratio between the steel, ratio between the Young's modulus of steel over Young's modulus of concrete, ES over EC, okay? And say if you forgot, right, it's roughly equal to 8, but here, be careful, you have the 5,000, okay? So in the lecture notes, we probably didn't write down explicitly, but remember there's a 5,700 square root of prime C, square root of prime C, then divided by a 29,000, and be careful with the unit, okay? This is KSI, okay? So this is going to be in PSI, okay? You bring this number in, it's going to be in PSI. So you better multiply by 10 to the 3 to convert it back to, oh, did I do it wrong? I did it wrong. Yeah, sorry. Let me clear this part. Here, clear drawings, eraser. Okay, so I think I reversed it, okay? So if we were to do this, so on the top, it should be ES, right? So 29,000 KS at the top. So 29,000, this is KSI, but we convert everything back to PSI. So don't forget to multiply 10 to the power of 3. Bottom here should be 5,700 square root of prime C, and that should be already in PSI, right? So this will be how you calculate it. And if you forgot anything, right? If you forgot everything and just don't want to go back to the equation, which you shouldn't, but if you happen to do that, you can throw a number in, which is 8, right? Throw a number in 8, and I gave you 1 point out of that, right? So not bad a deal, right? Not too bad of a deal. Okay. All right, so moving on, let's take a look at this. Now, this is the hooked bar for the development lens. Now, we did not talk about hooked bars, right? We talk about straight bars. So anticipate that in the problem that bars will be replaced by a straight bar. But rest of the things should still apply. But be careful here. Now, we have something called shear, right, in this problem as well. So for number 4 stirrup selected resist shear, what is the minimum spacing of the cycle for the stirrups? You do not see the stirrups, but they were asking to calculate the spacing of the stirrups. So there's a shear, partial shear problem in this, right? But the most important thing is the required development for a straight bar, okay? For a straight bar in the column is what? What is the required straight bar development length? Now, in the lecture, we have talked about two things. One is using the simplified approach to calculate this, and one is to use the conventional approach to calculate this. Now, the conventional approach is long. We showed the equation, right? So we ask you to do comparison. So in the finals, you probably see something like that as well. It will be a comparison, okay? Not just one method. So please make sure you understand how to do this in both methods. Now, one thing I have to tell you that this whole thing is a bare bar, no mentioning of a coating. No mentioning of coating, right? The only factor that you might have to worry about is that it's over 12 inch of concrete buried underneath the bar, okay? So 12 more inch of concrete buried underneath the bar. So remember there's a 1.3 factor for that, right? But think about what if I have coating, say epoxy coating, right? So there will be a coating factor of psi E, and that has to be 1.2. 1.2, right? So if you forgot all about it, don't worry, go back and see your notes, okay? Prepare yourself for this. Now for the column, right? So we show the column during the lecture, and this is pretty much it. That's it. This is the problem, right? We show how to solve this problem, and I use the more like a leaving the blank type of format for you, so to fill the number in. So best that you can go back and start filling the number in, but what we talked about in the lecture is this problem, right? So I have two axes, 1, which is the strong axis, 2, which is the weak axis, right? We gave you the concrete cover, gave you the materials, 5 KSI concrete, grade 60 steel, and we're trying to find phi P naught for pure axial loading, for balance failure, for zero tension point, and give you the compressive zone, asking you to find out phi PN, phi MN. So the final is pretty much similar to this, but the section will be different. Section will be different, so you have to use different numbers, of course, and be careful about the point, right? Be very clear about which point we're asking. Is it axial? Is it balance failure, zero tension? Whatever points that we were asking, go back to your lecture notes, find out that point, okay, and do it like that. Do it like that, okay? All right, last problem is a deflection problem, right? We talk about this, and you see this in the homework number 8 in the first problem. Again, it's not be turned in, so don't worry too much about it, but you still need to do it so you know how to do it. If you don't, go back to the lecture notes, right? We gone over the problem extensively. But this is a T section and no compressive reinforcement. No compressive reinforcement. Now, during the exam, it will be even easier. Okay, during the exam, it will be even easier. We will not test you the T section, right? I said, and we promised that we're going to test you only the rectangular section, but it might have compressive reinforcement in it. So if you don't know how to do compressive reinforcement, we're talking about IGT, ICR, and all that stuff, better go back to lecture notes, review it. And there's an extra page that I upload on Canvas, right? Talk about specifically how to do it in a compressive reinforcement setting, right? Doubly reinforce the section, right? So go over those, and if you don't know how to do it, come back to me and we can work something out, okay? But as you can see that given the section, given the property, given the reinforcement, we're asking you to calculate IG, ICR, MCR. Now here we use IG, okay? Now there's no IGT here. Now the difference between IGT and IG is that IGT is a transformed. That means that you have to consider reinforcement to convert that to concrete and taking that strip into the consideration, the little wings we're talking about, right? But here's IG, that means you don't have to do that, just use the gross section. But in the final exam, right, we may throw you IGT or IG, depends, right? So be careful what you read here in the subscript. It's actually very important, okay? Be aware of that. All right, now determine the effective moment inertia, i.e. consider full dead and live load, right? So how do we calculate this? We use the moment of inertia, right? Sorry, we use the moment, which is MA. So you need to get a moment diagram first, okay? So this is a little bit troublesome. You have to get a moment diagram, and you have to calculate MCR and get your effective moment inertia. If you forgot how we did that, go back to lecture notes, and we have a very detailed example of how to do that. Okay. All right, so this is instantaneous dead load deflection. Apply the dead load, use that equation we have in the lecture notes, you got a deflection. Once all the loads apply, compute instantaneous live load deflection. So how do we do that? Remember that? Okay. Now, lucky we did not ask you guys to do long-term deflection in this problem. Okay. We did not tell you like what is the sustained live load, how much is the sustained live load, and what will be the deflection in, let's say, 6 months, 60 months. We didn't ask any of that, but in the final we might. In the final we might. And there is extensive detailed explanation how we did that in the lecture notes. Okay. All right. So as you can see that's all. That's all the problem we tested in 2017. It's not that bad. In essence, is that I anticipate you finish this problem if you have, I mean, for your case, if you have a good understanding of it, 45 minutes top. 45 minutes top, and you have more than enough time to go over and check and make sure you did right. And if you have questions and problems, you can also refer to lecture notes and help you finish this exam. All right, so what I really want to comment on is one habit that I've observed in exam 1 or 2 is that students always wait till the last minute, right? They have too much a commitment to other things, other courses. Everybody's rushing in. Since this course, we have provided a lot of materials. We have videos, we have lecture notes. It's open book. Why don't I just wait till the last minute and bring the numbers into the equation, plug the numbers, just follow the procedures and lecture notes and deliver the answer? Why don't I do that? You shouldn't do that is because this problem we engineer in the final exam is different from the homework. In essence, is that it's not just a number game. All right. What requires you to get a full score, full points on this problem is that you need to understand why we're doing this, not just blindly follow the procedure. Okay, we have about a few students. When I say few, really like 3 or 4 students. I see them constantly just take the equation from lecture notes, plug in. Running out of time, don't know, don't care, and oftentimes they give a very ridiculous number at the end of the solution just because there was not so much a thought process going behind it. Okay, so I suggest to review for your finals. The best way is that you review the lecture notes, kind of understanding what it is, pull out a problem from your homework or from your just the lecture notes, any problem, rework it through by yourself. Try to rework it through by yourself, right? Understanding why this step has to be here, why this step is first, why that step is later, right? That has to be determined by you and be familiarized by you. And then before you know it, you know how to do the problem, right? And I can throw you any number and won't throw off your game, right? Won't throw off your game. So this is so much I want to say about final exams. Okay, I'm gonna stop sharing here and pause quickly here to tell you that the final 3 hours, okay, 3 hours, and it will be roughly the same amount of problem as you just seen right now. All right, I tested myself. I have made a problem already, and I tested myself. I did do it within like 25 minutes. I think that's my mark, but I know the answer, right? So it's not fair. So you guys should take a little bit more than that. So if I give you 1 hour, and that should be adequate, you have 2 more hours to examine your exams. This is the final, so think of it this way. This will give you the final grade. So just be careful. Take your time and go through the proper steps and make sure your calculations are right. Okay, I got like 2 or 3 students. I know who they are, and you probably know yourself. That during the second exam, they did everything right, but on the final number, they just somehow couldn't get it right. They were just 20% off, sometimes 30, 40% off due to some running errors in the middle, due to some missing steps. And those could really kill it because I have to deduct points, right? If I see a wrong answer, although I gave you a lot of partial credits already for that. Okay, so try to do a perfect job in the finals, make everybody happy. All right. Okay, so that's about the finals. Let me pause here. Any question from the folks? Any question from the audience? Anything? We are confident about it? All right. Okay, well, if you haven't started reviewing it, the course content, please do. Please do, okay? I'm pretty sure some question may jump out when you're reviewing the materials. And like I said, I made finals already. It's quite different from previous finals, okay? The format's changed a little bit in terms of the figures, drawings, but the essence is still the same. And there will be 4 problems, okay? 4 problems. I can tell right now it's gonna be multiple choice for problem 1, okay? And we'll have 1 development length calculations, 1 development length calculations. We have 1 surface deflection, that is deflection calculations, and we have 1 column analysis, okay? Column analysis. It's truly analysis, right? We don't do design for column, it's truly analysis. When I say analysis, right, you need to find out the PN, the MN, and the phi, right? That's all we need for the column. And it will be 2 axes, right? 1, 1, 2, 2, strong and weak axis, and we'll tell you which point we're going to find, we're trying to find, and you will do the calculation accordingly, okay? All right, so that's all about the finals. Let me quickly switch gear, come back to see the textbook about the design aid, design drawing, okay? We're way here, okay? So if you see the screen, this is on textbook, okay? I have the electronic version of it. If you don't, that's fine. But if you go to the appendix, there's a appendix A, design aid, appendix A, design aid. And in the design aid, if you go to page 1095, you see these are the column design aid, okay? Okay, column design aid, 1094 actually starting. All right, so I want you to understand how this drawing was obtained, and I want to explain to you a little bit what about this drawing, right? So this is design aid drawings, right? So it's a grade paper, and we have these envelopes, solid line here. We have these projections, solid line here. We also have these projection dash line here, right? So that's all about it. We have nice labels and everything. So first thing I want you to pay attention is the right top corner here. Right top corner here is our section. Is our section, okay? So in this section, everything is representative, has been symbolized or normalized. So it gives you the height of H, okay? And it give you a gamma H. Now, what is gamma H? Gamma H is the distance between the 2 layers of reinforcement, okay? So you only see 2 layers of reinforcement, okay? And now the width of the column is B, right? And it tells you that I'm designing, so this drawing was determined or finished with the concrete strength of 4 KSI and yield strength of 60 KSI. And gamma equal to 0.6. That meaning the distance between the top and bottom reinforcement is 60% of the original height. Okay. Now, very crucial, you see that there's a P, which is the force that exerted here with respect to the axis this way, okay, axis this way. And you should know it, this is the strong axis, right? Strong axis, because it has the height direction going this way, right? So it tells you that we're doing the drawing based on the strong axis, and there's eccentricity E here, showing here, okay? So that is the explanation of this. So you see that everything's normalized with respect to H, B, so meaning there's no number, no specific number for the section, meaning you just need to know the number and plug them in. How? Here's how. So on the x-axis, it's the phi mm, bending moment, with the stress reduction factor phi in front of it. And because of that, that's why this envelope looks different. This envelope looks different from the envelope we show in the lecture, because the envelope we show in the lecture has not been factored yet, right? So this has already been factored, so you see a different shape of envelope. That's fine, but take a look at here. There's a BH squared divided by Vmn. So everything has been normalized with respect to the section, meaning you can utilize this curve to find the point on the curve and to calculate the actual number given the size of the section, B or H and everything, okay? So that's called a non-dimensional interaction diagram, okay? That's why it's called non-dimensional, okay, interaction diagram. All right, so the x-axis is bending moment. The y-axis is the axial load, Pn. All right, so that's the axis. And now what about this drawing? So first thing you should see is rho G. Now what is rho G? Rho G is the reinforcement ratio. Rho G is the reinforcement ratio. That means how much reinforcement you put in the column. And then this way is different from flexure. This means total reinforcement. Doesn't matter is it compressive or tensile. All the reinforcement area divided by the entire section area, you got this ratio, okay? So each line, right? For example, this outside envelope is drawn according to a rho G equal to 0.05, Okay, so this line is drawn with respect a reinforcement of 0.05, okay, 5% of the whole cross section, Okay, all right, now you start to see these lines, right? So the first horizontal line, where this coming from, right? Where this coming from? This is actually the pure axial loading, pure axial loading. So remember the 0.85 and the K F prime C and FYAST, right? The compression, pure axial compression force. That's what this one is. Okay, and you go back here and all these drawings indicate in different regions. Okay, now your job is not to draw it, it's to understand these drawings, right? So this envelope is the interaction diagram we developed in the lecture, but with the phi stress reduction factor multiplied in front of it already. Okay, so this is the envelope. That means if I want to use the envelope to calculate the capacity of my column, I can do that. How do I do that? This is how. So I plug in all the numbers, right? I plug in all the numbers. Okay, so I want to point out at which failure, right? So if it's pure axial loading, I want to go to here, find out the pure axial force. Okay, if I know the eccentricity, here's the tricky part. If I know the eccentricity of the loading, right? Eccentricity, I can go along these lines, which is eccentricity divided by height ratios, and find out the intersection of these lines on this point to find out my axial force and bending moment. Okay, axial force and bending moment. All right, okay, now, in addition to that, right, now we shrink the envelope with reduced the reinforcement area, that's fine. And you see that there's a small symbol here said Fs equal to 0. Fs equal to 0 is almost equal to the approximately equivalent to our 0 tension point. Okay, so this is where roughly B is at. That means that the tensile stress in the reinforcement, Fs means the stress and reinforcement, right, equal to 0. I mean, this is close to our 0 tension point. Okay, all right. Now there's also another line indicating where my tensile stress in the reinforcement has reached the half of the yield strength. Okay, so this is so-called a point, another point, but this is not our C. Okay, our C is right here, compression control limit. So this is where our C is at, meaning the stress in the steel has yielded. Okay, which is the compressive control limit. This is C. Okay, now going on, there's a tension control limit, which is the point D here. Okay, this is the point D here. All right, and then at the end of it, this is pure bending moment, and they give you the number as well. Okay, so this is the design aid. This is design aid. Now, how to use this design aid? Okay, this is how, right? I have a column. I want to find out what is my axial force and moment capacity, right? So what I do is I give the section details, okay? And I give the eccentricities, right? I give the reinforcement area, everything. I can go back here and find out what is the envelope diagram is, okay? And then once I find out the envelope diagram, I use the eccentricity. For example, if the eccentricity is given 10% of the height, I follow this line here and see where it intersects. If it intersects here, I directly can read out the axial force and the bending moment. Okay, so that's one way to utilize this diagram here to estimate or to calculate the capacity of the column. Okay, there's another way. What is the other way? So in normal calculation, we use softwares, right? So there are Risa 3D, AutoCAD, and there's a desk robot, Autodesk robot, all these things, right? So they can actually do structure analysis and design now. There are more sophisticated software out there in the companies, right? So when I was a design assistant structure engineer, what we do is that they just produce a section, and my job is to hand check one of the critical member my senior has picked out for me. So what I did back then is to go back to the design chart, right? And I take a look at the section and I take a look at the axial force and the distance that is away from the center to give the eccentricity, right? You say, how you calculate that, Bob? So I will be given the axial force and the bending moment for the column, right? So I utilize the axial force and the moment to deliver this eccentricity. I can calculate that. So with these two numbers given, I'll go back to see where I falls, right, on these curves. And for me, if I just do a manual check, I don't even need to know exactly where I need to fall. I just need to know, for example, if I know the given area for the reinforcement. I just need to know if this P and M is falling within the envelope or outside the envelope. Okay, let me say this again. I just need to bring the number in here and to see if my P and M is falling within the envelope or outside the envelope. If it is within the envelope, then I'm fine. I'm set. I'm safe. My design is okay. But if the point is falling outside the envelope, then I have a trouble. I have a problem, right? It does not provide me the safe capacity. Okay, so these are just two easy ways how you can utilize this design aid. And there are thousand ways to use that, right? People do crazy things with them back in the 80s, and we still use them, especially myself sometimes if I do a simple structure analysis with some of the concrete members we test in the lab. But for this, this is not a homework. This is not like a official in the curriculum. I just like to introduce you to that. And so in later days, if you go to design office, you will take a look at it and you will hear story from your seniors how to utilize that, hopefully. Okay, but these are very useful, powerful design tools, right? So if you scroll, I keep flipping the pages, you can see different, right? These are different. Now for here, it increase the distance between the reinforcement, right? So I keep going, then my gamma increases, my plot changes, keep going, right? It changes again, 0.9, right? So these all changes start changing different concrete compressive strengths, right? And this is again concrete compressive 5 KSI, right? 6 KSI, go on, etc., so on and so forth, right? There are a lot, quite a bit, right? And they're very helpful. They're very helpful in actual design facility. And these are circular columns, right? And these are very helpful because, for circular column to do the distance is quite intensive compared to the rectangular column, because you can put a lot of reinforcement, and each reinforcement will have a distance, right? Each reinforcement will have a different layer of steels, right? So you can see that there's a lot of information here. Okay, we're done. All right, so this is what I want to introduce. So in the design office, you don't have to really do all the points on the envelope diagram. All you have to do is go back to see this diagram and see how you utilize that to get your number, or just to check if your number is safe or not. Okay. All right. With that, I closed out all our lecture content. Okay. Everything is done. I'll post the video again, but today apparently we don't have any notes. Okay. So you should be able to start reviewing now, and don't forget to fill in the CET evaluation. There's one extra points will be added directly to your final grades after weighing percentage. Okay. So that point is worth a lot. And that point is given under the condition that if 70% response rate is obtained, okay? 70% response rate is attained, okay? And please give me your suggestion and comments towards improvement of the lecture as well. I really appreciate it. So at the end, I just want to say that it's an extraordinary experience, okay? It's definitely not the best because we don't have the in-person, right? Unfortunately. But I felt like from the homework feedback and from quizzes and from the exam that you guys learned quite a bit, and I'm very happy with overall performance. Hopefully the final will not disappoint me, and I'll see you guys to be a future engineer in your jobs, okay? And thank you very much for being patient and being understanding and being diligent at your work, and I really appreciate that, okay? All right, so I'm gonna close out here and wait for any questions. If not, I'll see you next semester, all right? Thank you, and bye.
Professor.
For the course evaluation, are we supposed to do both of them?
I'm
or
sorry.
just the one for the class?
If you are registered both, you can just pick one. I would say that if you register for the main and the design lab, just do the main. That's fine.
Okay.
Yeah, thanks. Appreciate that.
Professor,
Yep.
for the
Yep.
design lab, is it individually turned in, or is it just one person in the group?
If you guys have 4 members, just one submission, but list all your members.
Okay, thank you.
Yeah. And if you want to submit individually, that means you can have one copy. Just everybody submit the same copy. Then I can tell, I can see that and give you the grade accordingly. That's all right. Either way is fine. Okay.
Dr. Wu,
Yeah.
I emailed you on Monday about needing to change the final for me. I was wondering if you got it. I hadn't gotten a response yet.
Oh, okay. Let me check. Oh yeah. I got your email. I just haven't got the time to arrange it for you yet.
Okay.
I'm going down the list. You're probably next. I have one student before you. I try to group you with another student. Okay, so
Okay.
let me check his availability before I do that. Okay, I get back to you, say, latest by Friday this week until he responds, but you know, I'll let you know. Okay.
All right. Thank you.
Yeah, not a problem. Yeah.
Hey, do we get extra credit for filling out the evaluation?
Yes. So that was a deal, right? We made a pact that if 70% of the entire class signed up the evaluation, everyone get 1 extra point towards the final grade. Okay, so that means if 70% of us, you know, response rate from the CET evaluation, at the end of the lecture, when I was finishing grading everything, adding up everything, decide to give you the letter grade, at that point to your final grade to bump up your grade, hopefully.
Okay. All right. Thank you.
Not a problem. Yeah.
For our lab design, what hand calculations do we need?
You don't really need hand calculation if your Excel sheet does a fantastic job. But if you feel like your Excel sheet only give you the component, you still need to add things up, you can do that. But you just need to show the design. That's essentially it. When I say show the design, is that you just need to tell me you got a VMN, you got a VVN, and they come from somewhere, right? You cannot make the number up, right?
Right.
Right.
Okay, thank you.
Yeah, not a problem. Okay, Andy and Calvin, you guys okay? You guys doing all right? Calvin, you there? Okay. All right. Well, Calvin, if you didn't hear back from me, if you need to talk to me or anything, let's talk about it, okay, next week or something. So I'm gonna sign off right now, okay? And I wish you good luck in the finals. All right, thanks.